Hello, my name is Hideo Nagahashi, and today I want to talk about the application of matrices, namely application to cryptography. So for example, suppose you want to send some secret information to your friend. Say like by email or just the whatever method, but it's possibly someone could see it. Okay? Okay. So in particular, like nowadays, when you just purchase something in the internet by using credit card, so you have to just send the credit card number to the company, but somebody might cheat, see it. So to avoid this, so instead of just directly sending the information, you want to encode this information to something else. Okay? Then you send the code to the receiver. Then the receiver now receives this the encoded information. Then they decode to get the original information. Okay? So instead of doing this, so you might want to do this for the security purpose here. Okay? Then there are many ways to do this. Then we can use matrix operation to do this. Okay? So for example, suppose you wanna send a message like done. Okay? So just 4 letters here. Okay? Then so suppose the sender and receiver just share some information, like say A corresponds to 1, B corresponds to 2, up to, so Z corresponds to like a 26. So there are 26 alphabets like this. Okay? So first of all, so you just put this in the matrix form like this. So like a column by column, or I just whatever way, but you just the sender and receiver just have to share the rule, and then now you change this into the 2 by 2 matrix by using this. So correspondence. So 4, 14, 15, and 5, right? Okay. So let's call this X. So now. So your info. So at least you're still in this level here. Okay? So now, if you just simply send this, so this is still like easy to break. Okay? So now, for example, let's use this is still simple, but so suppose you just encode by using like this kind of operation. So let's say AB. Like 4, 3, 1, 1. Okay? So then using y is equal to x plus a. So you can encode. Okay? So this matrix to y. So let's compute. So y is equal to x plus a. So x then a. So then so you send 8. Okay? So this the addition is entry-wise. Okay? Okay. So this is your y. Okay? So instead of sending the original message, so what you really send to the receiver is the matrix y. Okay? So now, so your client just receives the matrix y. So now he wants to get back the original, the matrix X. So how does he do that? So this is the the equation here. So given y, so he doesn't know this x, but he knows this. Okay? So he and you share this a, okay, in advance in some other method. So if you want to do that, so of course you just solve this one for x. Okay? So he can now obtain the original x by now subtracting a from the what he received. Okay? So y is this, then a is 4311. Then he can get the 4, 14, 15, and 5. Then, of course, now he has to do the 2 more steps. Now he has to just change this back to the BNOE, and then so he has to know this rule. But then finally, so he can get back. Okay. So this is probably more secure than by sending the information directly, but it's still, the addition is so simple, right? Okay? So if it's simple to compute, then it's easy to break. Okay? So that's why probably the better way to do this is use the matrix multiplication which we just ran. So as a next example, well, let's still use the same one, but let's use the different the formula to encode. So let's use multiplication now, okay, to encode the x here. So we still use x and a. Okay, so this time, so you multiply a 4311, okay, times x 15. Then remember using the definition of matrix multiplication. Okay? So now you can compute y. Okay? So remember the 43 times 415. Right? So now since this is not the issue here, so I just skipped the detail for that. But you want to check, okay, how to multiply. Okay? So let me write the result. So that's 61, 71, 19, and 19. So this is your new y. Okay? So now your client receives this. So then again, receiving y, so he wants to get the original x. So how does he do? So it's similarly, okay? So from y equals to ax, so he wants to solve this one for x. Okay? So the naive idea is you just simply divide by a, but remember the matrix multiplication is not commutative, so that's why you can't use this notation. Okay? So this is not clear what it means. This could be b times a inverse, or this could be a inverse times b, but we know that they are not equal here. So to make this idea the rigorous, so what you have to do is to cancel this a, you have to multiply a inverse, the inverse matrix from left. Okay. And then in this course, so we don't prove it, but although the matrix multiplication is not commutative, however, it is associative. So in other words, you can regroup. Like this, okay? So they are equal. And then we know that the A inverse times A is an identity matrix which is cancelled out. Okay? So the original idea is just same as the number. you can just simply solve this one for x as long as a is not 0. Then you can just solve for x, right? The same thing, but we have to be we have to be careful, yeah, to do that. So anyway, now so you get the formula to decode. So x is equal to a inverse times y. Okay? Then just recall that the formula for the a inverse. So this is something you have to compute from that. Let me recall the formula. Okay? For the inverse is given by this formula. Okay, so applying this formula, so now you can compute A inverse first, which is 1 over 4 times 1 minus 3 times 1. Then dA, so you switch these two, and then negative B, negative C means you just put a negative sign to that. Okay. Then this one happens to be just a 1, so you can just take it out. So your A inverse is just this matrix here. So finally, you can compute x. So x is equal to A inverse, which you just found, times y is what you receive. Okay. 19 and 19. And again, this is just the matrix multiplication here. Okay. Then again, you have to do it. Okay. Check this multiplication. Let me just write the result. But as we expect, no. So x, we already know that. So you should get this from here. Yeah. So 4, 14, 10, 15, and 5. So then from this, so you can just get back the original message done. Okay. Thank you.